So we talked about saturated and unsaturated. Other descriptions include dilute and concentrated. Dilute, these are relative. Dilute just means that they're a small amount of solute, and concentrated is a large amount of solute. And then we have many quantitative measures of solution concentration. So here's a table from your textbook, just summarizing the different types of units, and this might be helpful when you do homework. So molarity, we've talked about this before, back in section 4.4. It's the amount of solute in moles, always, divided by the volume of the entire solution in liters. Here's a refresher on how to make a solution. One of the problems with molarity is that it changes slightly with temperature, because the volume of the solution will be greater at higher temperatures. Because as you heat up a liquid, it expands slightly, and so that will change the molarity. Molality is a concentration that does not depend on temperature. So molality is independent of temperature. Molality is the amount of solute in moles divided by the mass of solvent in kilograms.
In the last example, we left it as small m, and doesn't that represent molality?
In the gas one,
Yeah, the one
that was a capital M. Yeah, and M's are hard, aren't they?
Oh, yeah.
So I believe what I wrote was this. So the underline means it's a capital M, but that's a good question. Underline means it's capital M. So again, with the amount of solute in moles, but now the mass of the solvent in kilograms. And the mass of the solvent does not change with temperature. So molality will be the same at any temperature. It's important to note that this is kilograms of solvent, not of solution. Most of the things we talk about is the whole solution. We have parts by mass and parts by volume. So we take the mass for parts by mass. It's the mass of the solute divided by the mass of the solution multiplied by a factor. So percent literally means per 100. So this is mass of solute divided by mass of solution times 100%. If we have the percentage, say 14% by mass, that means that we have 14 grams of solute per 100 grams of solution. And so a percentage makes a great conversion factor. Parts per million, we're multiplying by 1,000,000. Parts per billion, we multiply by 1 billion. And these are abbreviated ppm and ppb. You'll see these a lot in like the water report that the city sends out about water quality. And it'll say, well, you know, the lead is this many parts per billion or whatever.
Do they change it to make it seem less?
Well, what they do is they use the unit that gives a convenient number.
Gotcha.
So they're going to say, well, it's 1.5 parts per million. They're going to say that instead of saying, well, it's 1,200 parts per billion.
Yeah.
Because you want reasonably sized numbers.
Mm-hmm.
So if you end up with 0.000000 parts per million, then you're going to go to a smaller unit so that you get a nicer number.
Gotcha.
So if you're dealing with parts per million or parts per billion, it's that many parts for parts per billion, this many parts per billion parts. And the part could be gram, it could be ounces, kilograms, pounds, anything. It's a mass unit, but as long as the mass units are the same, it doesn't matter. So 15 grams of solute per billion grams of solution, but you could also do it in pounds or kilograms. Parts by volume is the same pattern with multiplying by a factor, but we're looking at volume of solute to volume of solution. So 22% ethanol by volume means 22 milliliters of ethanol per 100 milliliters of solution, or 22 liters per 100 liters. What mass of sucrose in grams is contained in 355 milliliters of a soft drink that is 11.5 sucrose by mass? Assume a density of 1.0 grams per milliliter. So this is using the percent concentration. I'm a big fan of dimensional analysis, if you haven't noticed. And so I generally look to see if I can do dimensional analysis before I would look for a formula or an equation. So here, excuse me, we got a bunch of numbers. We've got 355 milliliters. The 12 ounces is in there just to give you a reference. We're talking about a 12-ounce soda can. 11.5%. And then we've got a density, 1.04 grams per milliliter. Then we have to think about, okay, this soft drink has sucrose in it, that's table sugar. And what's the solvent? Water. Water's, you can generally assume that water's a solvent unless it's otherwise specified. So we've got parts here. There's the solute, the solvent, and the solution. So this 355 milliliters, is that referring to the solution, the solvent, or the solute? What do you think?
Solution.
Yeah, that's the solution. What are the tables made of? I'm not sure. That's a random question.
I was thinking like, it has to be something that doesn't really react.
Yeah, the bench tops are pretty impervious to most things, but as you can see, there are things that will damage them and eat them. They don't like red hot crucibles being set on them, for one thing. Okay, so we decided, back on track here, that this is the solution. 11.5%. That is 11.5 grams per 100 grams, right? Yeah, that's a lot. 11.5 grams per 100 grams. Grams of what? It's 11.5 grams of sucrose per 100 grams of what?
Solution.
The solution. It's the whole solution. Most concentration units are per whatever of solution. And then down here, we've got 1.04 grams per milliliter. The density. This density is referring to what? The density of sugar, the density of water, or the density of the soda?
Solution.
Yeah, the solution, the whole soda, right? Because we know the density of water is 1. And the density of sugar, well, that's not a liquid, so yeah, this is the solution. So that means 1.04 grams of the solution is equal to 1 milliliter of the solution. So now we've identified what all these things are. What are we trying to figure out?
How many grams of sucrose we have?
Grams of sucrose. So over here, grams of sucrose. That's what we're trying to get to. So we have to figure out which of these we should start with, and then how we can get from one of these over there. So, speaking to those who are dimensional analysis challenged, right? How do you decide? Well, the units are a big clue. This is something per something. This is something per something. This is just milliliters. So we're probably going to start with that one because it cannot be used as a conversion factor. So I'm going to start with milliliters, and then I'm going to see how I can get to this other one. And I'm going to use these two guys as conversion factors.
So then you do the density.
Yeah, so this one has milliliters of solution in it, so I could use this to get to grams of solution. So I'm going to go to grams of solution. And then I'm thinking, since this is the only one left, this is probably the next one. Here we've got grams of solution and grams of sucrose. Oh, that's grams of solution and grams of sucrose. So we can go like that. Okay? So once we've got our path written out, it should be pretty easy after that. So 355 milliliters of solution. My path has 2 arrows, so I need 2 fractions. So I'm going to have grams of solution here, and then I'm going to have grams of sucrose. Just following the path. Then I look at this unit, and I want to put that unit down here. So this is your review of dimensional analysis. It's going to show up on the final, guaranteed. And then I'm going to put grams of solution in the denominator here to cancel out. Work out all the units, and then stick the numbers in. So here I've got the grams of solution and milliliters of solution. So I'm going to use the numbers here. 1.04 goes with grams of solution. So that goes on top, and the 1 goes on the bottom. Here's grams of sucrose and grams of solution. So that's this one. Keep the number with the correct unit. And then we multiply and divide. 355 times 1.04 times 11.5 divided by 100. How many significant figures should this have? 3. So 42.5 grams of sucrose. Is that a lot of sugar? Yeah, it is. So somebody yesterday shared this interesting tidbit with me. That's about a shot glass full of sugar in a 1 12-ounce can of soda. That's why it tastes good, yeah. Personally, I like the taste of sugar, but that's a lot of sugar. Anyway, any questions about the process? Yeah, some of them have more. And it's right there on the label. Personally, I like sugar-free energy drinks.
Some of those energy drinks that you guys drink, I can't have them. Contain about, I look at carbohydrates, not sugars. One of those little cans of energy drink is about the same as you can put along a Subway sandwich.
Really?
Yeah. Same amount of carbs in that little tiny can.
Well, I've got a big can, and it doesn't have any carbs.
Big.
Yeah. But yeah, there are some. They may not have sugar in them, but there's other things that can give you carbohydrates. And you know what your body does with any carbohydrate? Turns it into sugar. And then if your body has more sugar than it needs, it turns it into fat and stores it for later.
When you keep you warm.
Keeps you warm for
When you have to keep track of carbs, you know that sugar-free doesn't mean carb-free.
That's true. Sugar-free does not mean carb-free. Yeah. So there's actually a lot of chemistry involved in nutrition. I don't want to say dieting, but being concerned about what you eat. There's a lot of chemistry involved in that. Okay, so another type of concentration unit, mole fraction and mole percent. And we've seen this guy before, right? This Chi. Do you remember where we saw him?
At the ball. Greek. Oh, hey, Kai.
Hi, Chi. Yeah. No, we saw him when we talked about partial pressures. So this is mole fraction. So the mole fraction looks at the amount of solute in moles divided by the total amount of moles in the solution. But you can't just, like with mass or volume, you can just measure it. With moles, you can't just measure the moles of solution. You have to look at the individual parts. So it's the moles of solute and the moles of solvent added together. So another way to express it is this, N solute over N solute plus N solvent, where N represents the amount in moles. So that's mole fraction. Mole percent is just the mole fraction times 100. Okay, so this is a fun problem. A solution is prepared by dissolving 50.4 grams of sucrose in 0.332 kilograms of water. The final volume is 355 milliliters. Calculate the concentration of the solution in each unit.
11.5%.
You might think, well, 11.5%, but look, this mass, this is a soda, this is probably a soda, that has more sugar than the other one, so we can't just use that. But molarity. So when you do problems like this, you need the molarity. Ask yourself, well, what does molarity mean? Moles over liters. So I'm going to write that down. Molarity equals moles divided by liters. Liters of solution. So then I need the moles of the solute and the liters of the solution. Well, they gave us a mass of sugar. 50.4 grams of sucrose. Can we figure out how many moles that is? So we're going to put in the molar mass so the units cancel out. Well, we got to figure out the molar mass. 12 carbons times 12.01 plus 22 hydrogens times 1.08 plus 11 oxygens times 16, 342.3. So 1 mole of sucrose weighs 342.3 grams. So 50.4 divided by 342.3, 0.147. So we should have 3 sig figs. I'm going to cut corners a little bit today. I'm only going to throw in 1 extra digit. Just living on the edge, right? What are you thinking? Moles of sucrose. So that's what goes in the numerator. It really is not a good idea to round off intermediate calculations to the exact number of sig figs. And then volume of solution. Well, they gave us the volume in milliliters. How many liters would that be?
Like
0.355. How do you know it's not 355,000? Because the smaller unit should have the larger number. The larger unit should have the smaller number. Or think about, we've done things with milliliters in the lab, right? Can you envision a 10 ml graduated cylinder? A milliliter is a little tiny bit, right? It's actually a cubic centimeter. How big is a liter? Half a 2-liter soda, right? So could 355 milliliters be 355,000 liters? That's pretty ridiculous. That's like saying 1 inch is equal to 12 feet. You've got it backwards. Anyway, that's one of my soapboxes. I'll get off now. 0.355 liters. If you're inclined to make mistakes like that, write it out and use your calculator. I see people on their lab reports dividing and multiplying by 1,000 and not moving the decimal point enough places. It's okay to use your calculator. So this comes out to be 0.415 molar, capital M. That doesn't sound too bad. 0.4 molar sugar solution. It's a lot of sugar. How would we do mole fraction? What does mole fraction mean? The moles, in this case of sucrose, divided by the solute and the solvent. So the moles of sucrose plus the moles of water. That's the mole fraction. Well, we already have one of these numbers, the moles of sucrose. So I've got 0.1472 moles. And I've got 0.1472 moles up here. How do we figure out the moles of water? Well, they gave us a mass of water. This is the volume of the solution. So we can't just use density and do that, but we can use this. Whoops. So 0.332 kilograms. How many grams is that? 332. So 332 grams of water. And now I need the molar mass of water, grams on the bottom, moles on the top. I've got that one memorized, it's 18.02. So 332 divided by 18.02. Again, this should have 3 sig figs, so this is 18.4, and I'm going to carry that extra one. So that goes down here, 18.42 moles. When you're keeping track of significant figures and you've got dividing and adding mixed together, you need to be cautious. So look at the sum of this. So 0.1472 divided by the quantity, you're going to have to use parentheses here, 0.1472 divided by 18.42, I'm sorry, plus 18.42, close parentheses equals 0.00793. What are the units on that? So we've got moles on top and moles plus moles on the bottom.
Moles per mole. Per mole.
They cancel out. There's no unit.
Just get a number.
You just get a number.
Multiply it
A
later.
fraction is just a number. If you multiply it by 100, then you get a percentage, but right now it's just a number. When I add these two together, I'm going to get 18.5 something, and the uncertainty is going to be in the first decimal place. It's still going to have 3 significant figures, and this one's 3, so that one's 3. What would be the easiest one to do next? Mole percent, right? Mole percent is the mole fraction times 100. So, yeah, so 0.00793 times 100, 0.793%. So you look at that and you say, oh, well, that's not so bad. The mole fraction's only 0.79%. Big deal. But look at the difference in the mass of 1 mole, 342 grams versus 18 grams. Okay, what about, let's do percent by mass. So this is the mass of sucrose, so grams of sucrose divided by what? The mass of the whole solution. So that's the grams of sucrose plus the grams of water. And that is a place that students screw up a lot. And that's a place, you know, I usually say, I'm not going to try to trick you with this. I will try to trick you with that. I will. I'll give you the mass of the solute and the mass of the solvent and ask you for the percent by mass, and half of you won't add them together, and you'll get it wrong. Happens every semester. So here we need the mass of the sucrose, so that's 50.4 grams. And down here, we need the mass of the sucrose plus the mass of the water times 100.
Why does it say when, like, in the, oh, no.
Sometimes you're told what the mass of the solution is, but sometimes they just tell you the mass of each part.
You can maybe do that in the test.
Well, somebody has to, because I know somebody will. So 13.2% sugar. So you look at it by mass, it's a lot higher percentage. The soda is 13.2% by mass sugar. And this kind of points out, too, that how you report the numbers to an uneducated person makes them say, oh, well, this is fine. Well, no, it's not. You need to know what those numbers mean. Okay, molality. What's molality? Moles per kilogram. Moles of solute per kilogram of solvent. So moles of solute, we calculated that already, 0.1472. That's the solute. And the kilograms of the solvent, the kilograms of water, and they actually just flat out gave that to us, 0.332 kilograms. Um, 0.1472 divided by 0.332, molality is 0.443. I am not fond of the unit molality, and one of the reasons is for its abbreviation. It's an italicized M. How easy is that to mix up with meters?
Quite easy.
Very easy.
But in context.
Well,
think
yes,
about it,
but
you're not going to travel 0.443.
people have enough trouble with the capital M, meaning moles per liter. Yeah, this just adds to it. There's too many M's. Well, molarity is very, very useful to chemists because it's volume of the whole solution. So that's really easy to measure out. If I need 1 mole of sugar for a reaction and I have a 1 mole per liter solution, I just measure a liter of it, piece of cake. We deal with moles all the time because of stoichiometry. But molality is kilograms of solvent. So that's harder to use when you're just doing chemical reactions. The only reason that it exists, I think, is because it's not temperature dependent.
Have you ever noticed that you switch between fours?
I do switch between fours. Yes. Some of my fours are the closed pointy ones and some of them are the open ones.
And in the molality, you did both right next to each other.
And you know, sometimes it's just that I miss. So I think I form them the same way. I don't think I go like this ever. Sometimes I miss. I think that's what it is. I could tell you so many stories about students. Is that a 4 or a 9?
We both, that's why you had to. Oh, yeah.
So many students. I just, oh my goodness. Anyway, so any questions about the units? I'm super distractible today. It's terrible.
It's an ice cream.
Oh, here's another one. I know it's ice cream time. But we haven't even talked about colligative properties. We have to get to colligative properties. Okay, so this example I did yesterday. It's in yesterday's video. You can go look at that there.